Now let's see a switching expression. Whenever you want to design any electronic circuit, first the procedure is we form the switching expressions and then we minimize it and then we realize it. Realize it means implement it using AND gate and OR gate. Okay, what is AND gate, OR gate, we shall see it later, but the important thing here is if you have any switching expression, since we are going to convert it into a circuit, the smaller the expression, the better it is, because if the expression is smaller, the circuit is going to be smaller. So we are very often interested in smallest expressions in terms of either a literal. Literal means any variable which is occurring either in its true form means like a, or its complement form a prime, right? That is called a literal. So I'll just take an example and explain you. So first now see how does this switching expression look like, and then we shall see how to minimize it. So watch it. Switching expression is a finite number of combinations of switching variables. Switching variables means like A, B, C, D, which are supposed to take A, B, C, D or X, Y, Z, whatever, which are supposed to take only two values, which are 0 and 1, Boolean variables, right? Combination of switching variables and constants. Constants means in switching theory the constants are only 0 and 1 by means of switching operations. So any other operation can be implemented using these operations. Therefore, these are the basic operations or primitive operations or complete. They are functionally complete also. Functionally complete means any operation can be implemented using these operations. Plus, dot and not. If I have AND, OR and NOT gates, NOT operations, and if I have these Boolean variables along with the constants, and if I form any expression, that is called switching expression. Now what is the main purpose of switching expression is we will somehow convert it to a digital circuit. The smaller it is, the better. Now how can we know that a switching expression is smaller? Either we decrease the number of terms or we decrease the number of literals. So literals means check this in this expression. So these are all the expressions. Switching expressions look like this. Literals means 1, 2, 3, 4, 5, 6. So even though the variables are 1, 2, 3, the literals present here is 6. Every occurrence of a variable in its true or complement form is called literal. Therefore, I am going to count x, x prime and again x here. So 6 literals are there. Either you decrease the number of literals or you decrease the number of terms depending on your definition of minimality. We want to just simplify the switching expression. Now there are various methods of simplification, but the simplest method is we shall form from rules, some rules or formulas, and using which if we can directly simplify it, it is better. Otherwise there are various methods. All the methods are actually equivalent. Now let's see one method using just the formulas. Watch it. First one is properties for simple, and again one more thing, here also the principle of that duality can be applied, which means if you write a formula, the equation, then you could actually substitute AND with OR with AND, plus with 0, 1 with 0 and 0 with 1, and you can get the actual, whatever we did it. We can get the same kind of expression. Now, the first one is called absorption. Absorption means, see how it is, x is going to absorb the next term. So, how can you write this? X plus x into y. So, how can you write this one is, you could write it as x concatenated with 1, x ANDed with 1 plus xy. Then you could pull out x as common. Why? Because dot is distributive over plus. Using that rule I am pulling out x as common. Then what is remaining? 1 plus y. And you know that 1 plus y is nothing but always 1. So anything odd with 1 is 1. So what is this? Directly x. So it is proved. And even you could write the dual of it and the same thing will apply. If you write dual of it, what happens? X concatenate x and x plus y equal to x. This is the dual of it, right? So you can prove that this is also equal to this. Simply if you want directly prove it, just you multiply or just you add x with x, then you get x, and we add x with y, we get xy. Therefore this expression and this expression both are same, and anyway it is already proven to be equal. Duality holds there. Now what about this one? It is interesting. See, how are you going to prove that these two are equivalent is, now we already know that plus is distributive over dot. Therefore x plus y prime x plus x prime y can be written as x plus x prime and x plus y, and you already know that x plus x prime is 1. Therefore what is it? X plus y. So this one is equal to x plus 5. And here also duality holds. So what is the dual of this one? So how can you prove that this is right? Here you can use the rule of and is distributive over R. Therefore you could take this and you can multiply it, right? So I think yeah, and is distributive over R. So how can you do it? X into x prime plus x into y, this one. Now what is x into x prime? It is 0. 0 plus xy, which is nothing but xy. Got it? It is very important. Consensus theorem is very important and is very tricky to understand it. So what we wanted is, we want to simplify this, but in order to simplify it, we'll expand it and again simplify it. See how it works. See, if you had to remember this, definitely as a formula you have to remember this, or we shall practice lots of questions on this. Therefore I think automatically you will remember it. But then see how it works. X into y, I mean x and y, x prime and y and z, which means if there is a expression concatenated with some variable or concatenated with some expression, and then a complement of the expression concatenated with some other expression, and a combination of these two expressions, then these two are actually redundant. Redundant means you can remove them. So okay, one more way of saying redundancy is, just follow this. If the value of expression does not depend on any term, then that term is redundant, which means even if you have the term or even if you don't have the term, if it is not going to be of any difference, then you better remove it. That is called a redundant term. And now in this case, this yz is going to be redundant. So we shall prove it. We shall prove how it is going to be redundant. It is unlike the other proofs. Instead of when we are trying to reduce it, we'll expand it and then reduce it. See this, how it works. xy plus x prime z plus yz concatenated with 1, ANDed with 1, concatenation. See, by mistake I'm saying whenever I say and, I'm using concatenated. You please correct it. And now in place of 1, it could be x plus x prime. So it is xy plus x prime z plus yz into x plus x prime, that equal to, so now you can expand it out, xy plus x prime z plus expanded. See, in place of 1 I am writing x plus x prime. I think you understood how it is. It is already a rule. So x plus x prime is 1, that you must be knowing already, right? I am just expanding it out. Then what do I get? Yz into x plus yz into x prime. Then what is this? Check this. Now if you look at these terms, xy and then xyz, if you look at these terms, from these two, xy could be written as xy concatenated with 1. Therefore if you pull out xy from these two, this term and this term, what do we get? xy into 1 plus, what is remaining here? Z plus. Now from these two terms, if you can see that there is x prime z, right? X prime z. So x prime z is common in both of them. Maybe you can multiply with 1, and if you pull out x prime z from these two terms, then what do you get? X prime z, sorry, if you pull out x prime z, then what do you get? 1 plus y, right? So 1 plus z is nothing but 1, 1 plus y is nothing but 1. Therefore what do you get? That equal to xy plus x prime z, which means this one, right? It is very interesting and very, very important also. Not direct, you might not see that it is directly possible, but then if you can observe this, it is definitely possible. Okay, so the proof is, whenever there is y, or how to remember it is, in place of x and in place of y, sorry, in place of x and in place of x, there could be any expression, I just generalized it. I just put x, but in place of x and y, there could be any big expression. So even if there is any big expression here, and if there is a complementation of the expression here, and if there are two different expressions here, and there is a concatenation of those, I mean adding of those two expressions, always remember this expression is redundant. That is the what can I say, usefulness of this consensus theorem. So we are going to use it very frequently while minimizing the Boolean expressions. This so you just remember it, or you can derive it. Better you remember it. Fine. Now watch this. Simplify this. So given any expression, switching expression, we would like to have a as small expression as possible. Even if it is very big, I want to simplify it, right? So there are various methods. Maybe you could use the consensus theorem, or you could use absorption. Whatever you like, you could use. But finally, one more thing. There are various ways to simplify it, and whatever it is, the final answer should be same. Whatever I do, whatever I get the answer, and whatever you get, both of them should be same, right? Now here, if you look at this, it is very straightforward. It is simple that you are seeing z as common in everything. So pull out z as common. If you pull out z as common, then what do you get? Plus y plus x, isn't it? So it really matters when you are looking at TOC. In TOC, you should always pull, if z is here, you should always pull z from the right side, because in TOC, concatenation is not commutative, which means a dot b is not equal to b dot a. It is concatenation. But here the AND operation is commutative. A dot b is equal to ba. Therefore, either you pull out from the right or pull out from the left, it doesn't matter. So if the z is here, you could either pull out from the left or pull out from the right. It doesn't really matter much. Okay. And now see this. See these two terms. And second rule I am going to apply is, you could apply any rule. I am going to apply the second rule is, plus is distributive over AND. Therefore, I'll take plus and I'll distribute over AND. So what do I get? Z into x prime plus y into y prime plus y, which means I'm just taking this and I'm distributing over here. So y prime plus y and x prime plus y plus x, right? Then what do we get? Z into this entire factor is nothing but 1. Then what is remaining? X prime plus y plus x, right? And now x plus x prime is nothing but 1. So what is it? Z into 1 plus y. So what is it? Completely it is going to be 1. So whatever you got is z. Understood this? So this entire thing can be minimized to z. So we used luckily it is it is very simple that you could apply rules and easily do it. But maybe if the expression is very big, we would like to use some other methods. Later we shall see those methods. And one more thing, you might have got some other method to solve this, but the final answer should be same. You please check it. And next one is in switching algebra, you should remember that cancellations is inverses and cancellations are not allowed. For example, if you have a plus c equal to a plus b, if you have expression like this, some equality like this, then you should not cancel out a and a. And if you have a into c equal to a into b, then you should not cancel out these two. Okay, so you should find out the values of a and c, a, b and c, for which this equality holds. That is the meaning of it, right? You should not cancel out either, you should not cancel out or you should not do the inversing. So these two operations, these two are not allowed in the switching expressions, right? So I hope that you understood this simplification. Let's see more examples.